Okay. We were talking about CDMA. So just to remind you what's going on, basically every user gets a quasi-orthogonal spreading sequence. So they are not orthogonal, they're quasi-orthogonal, which means that the inner product between any two of these spreading sequences is not zero. It's small, but it's not zero. So the idea is that if you each user gets one of these spreading sequences and then transmits information with it. So for example, if everything is bit synchronized, what I see at the receiver, so let's let these spreading sequences be S1, S2, and so on up to SU for the number of users. So each user sends a bit. So what we have is, if everything is bit synchronized, in other words, all the users' bits start at the same time, which is not true in practice, but it makes things mathematically convenient. Then I have a bit sent by user 1, plus a bit sent by user 2, plus a bit sent by user 3, and so on, up to the bit sent by user U, plus noise. So here I'm using, actually I'm using these as vectors. So I'm dealing with this in signal space. So these are all these spreading sequences are vectors. So it's noise. So what I do is, let's say user 1 is the user of interest. Or excuse me, what we talked about last time was the case where things were optimal. So in other words, these are not orthogonal. This is these spreading sequences do not form an orthogonal basis. So what we did first was we orthonormalized the basis, expressed everything in terms of that orthonormal basis, and then we looked at the Voronoi regions, and we tried to analyze things as best we could using these techniques we had. What we saw was that in the two-user case, we got something that looked a little like this. This sort of skewed square signaling constellation. And what we showed was that, actually it's back, do it the other way. Skew the other way. Voronoi regions look something like this. That's not drawn very well, but you get the basic idea. So, in other words, the Voronoi regions are no longer rectangular, and we can't use the simplifications that we used before. So it turns out that as the number of users gets larger, by the way, this method of detection is called multi-user detection. It's called multi-user detection because each of these points correspond to the bits of both users. So this would be +1, +1. This would be +1, -1. This would be -1, -1. And this would be -1, +1. So each of these corresponds to the bits of both users. So you're trying to detect both users at the same time. Turns out it's simpler if, let's say, user 1 is the signal we want to detect. It's simpler, but less. Poorer performance to simply say, okay, user 1 is the one I'm interested in, so I'm only going to detect user 1, and the rest of this I'm just going to pretend is all grouped together with the noise. So we have interference plus noise that's all sort of muddled together. So it turns out this is, as the number of users grows, this becomes an NP-hard problem. But this, treating it all as noise, basically ignoring it, is as simple as single-user detection. So that's why it's done. So let's look at, last time we looked at multi-user detection, now let's look at suboptimal single-user detection. Basically what we have is this. We have, in the bit synchronized case, let's say we have two users, so their spreading sequences are S1 and S2. So what I receive is this. Alpha 1, that's the bit from user 1, where alpha 1 can take the values plus 1 or minus 1. So that's just a binary bit. Times user 1 spreading sequence plus user 2's bit. This is before the match filter. User 2's bit times user 2 spreading sequence plus noise. So basically what we do at the, what we talked about last time was this. We said the matched filter will do the following operation. So we'll have a normalized filter matched to the first user's sequence. Let's call that SX. And if we think back to signal space, what do? We take that signal and normalize it. And because these spreading sequences, we're going to deal with only spreading sequences where the chips are polar NRZ. So basically, every element of this vector is either plus 1, minus 1. So the norm of this is it can be thought of this way. Norm S1 is equal to S1 dot S1 square root. Because every element of S1 is plus 1 or minus 1, basically what I'm doing here is I'm taking each element of S1 and squaring it, and then taking the square root. Because they're all plus 1, minus 1, this is just the number of elements in S1. That's equal to the square root of NB. So Sx, the normalized basis function, is 1 over root NB S1. So if this is in the dot product form, this is my match filter. So the output of the match filter is y dot Sx, which is alpha 1 S1 dot Sx plus alpha 2 S2 dot Sx plus n dot Sx. So here's my noise term at the output of the match filter. This is my signal of interest. What is this? This is S1, excuse me. S1, if I look here, is root NB Sx dot Sx. And what's Sx dot Sx? So it's Sx is the normalized basis vector in the direction of S1. So because it's normalized, what is Sx dot Sx? It's just 1. So we get alpha 1 root NB. Over here we get alpha 2 times S2. So this is a different vector dot Sx. It is almost orthogonal to, but not exactly orthogonal to Sx. So this is not 0. So we can't eliminate this. It's some small number, and this is the noise term that we're